Hey guys, so in today's video we'll be covering Gibbs free energy and what that term actually is. I'll also be talking about how it can be calculated and in what conditions is Gibbs free negative and causing a spontaneous reaction. So typically we use Gibbs free energy to look at the difference in energy states of a chemical reaction. And typically this can be defined as the amount of energy after a reaction has occurred minus the amount of energy in that system before it happened. Another way to calculate Gibbs free energy is to look at the change in enthalpy of the system. And enthalpy is essentially just the heat, minus the change in entropy. Now remember, entropy is essentially just a term used to describe the amount of disorder that's in a system. And in this equation, we multiply the entropy by the temperature. And it's important to remember that temperature here is in Kelvin. So in GAMSAT, for example, you might get tripped up with converting between Kelvin and Celsius. So it's just important to remember that 0 degrees Celsius is approximately 273 degrees Kelvin. So a good trick that I used to remember what enthalpy was to look at the TH in enthalpy. And that sort of reminded me of a thermometer. And now thermometers are used to measure your body temperature or heat. So that's something that I used to remember, that enthalpy was just the amount of heat in the system. And like I said before, the entropy is just the amount of disorder. So a good way to think about this is we lose entropy when a system loses moles. So if we go from 1 mole of a compound to half a mole of that compound, we're losing entropy because there's less disorder or less chaos in that system. So something that wasn't immediately clear for me was that we could actually see the change in Gibbs free energy when we look at the standard energy diagram. So in this first diagram here, we have our initial Gibbs free energy here, and this little hump is essentially our activation energy, or the energy required for that reaction to occur. But ultimately here we have this decrease in Gibbs free energy. And what this tells us is that we actually lost energy when this reaction happened. The Gibbs free energy was negative. Alternatively, in this diagram, we see that we have this increase in the Gibbs free energy here, and we actually ended up with more energy after our reaction than what we started. And this shows us that the delta G, or the delta Gibbs free energy, is actually positive, and that reaction actually gained energy. Now, I think it's fairly logical to think about that. If we have to add energy to a system, that involves a lot of work. Whereas if we're just losing energy, if a system is going into a lower energy state, that would be much easier to accomplish. So in this first diagram here, because we're losing energy and we don't actually have to put any further work or further energy into that system, this reaction here is likely to be spontaneous. However, when delta G is positive, it's saying that this chemical reaction requires further energy to take place. And that's less easy than something that's spontaneous. So this is a non-spontaneous reaction. When delta G is positive, it's non-spontaneous. A good way is to link this to actually human biology, with adenosine diphosphate converting into adenosine triphosphate. So when ADP goes into ATP, delta G is actually positive, meaning that there was energy required to convert ADP into ATP. However, when we're starting exercise or we're moving our muscles, we need energy. And when we break down AD or ATP into ADP, we get a negative delta G, or a release of energy. And this allows our muscles to function as they normally would. So I guess one of the bigger questions in a lot of chemistry exams, as well as the GAMSAT itself, is you might be asked to determine when a reaction is spontaneous. And what this is essentially asking is, when is the delta G negative? So with these conditions here, we got 4 different conditions. In this first one, we have a positive enthalpy. That just means that heat, or the heat of the system, is increasing. And if we had a positive entropy as well, or the disorder in the system was increasing, we would expect a positive delta G. However, at very, very high temperatures, when this positive entropy can overcome the positive enthalpy, we would expect a negative delta G. So when both of these values are positive, the delta G will be negative at high temperatures. Cool. The other scenario is if we had a positive enthalpy, or a positive delta H, and a negative delta S. So in this scenario, we have a positive number minus a negative number, and that would just involve, or that would result in overall a positive delta G. So this one here would be non-spontaneous. When we start getting a loss of heat in the system, or a negative delta H, we can see that if delta H is negative, and we also have a positive entropy, meaning that the disorder is higher, it would be a negative number minus a positive number. So that would create an even greater negative delta H. So in this scenario, we would expect the reaction to be spontaneous. In the last one, we have a negative delta H, and we have a negative delta S. So if delta H was negative, we would need temperature times delta S to be essentially 0. So in this case, we have a negative delta G, or a spontaneous reaction, only when only when the temperature is equal to 0. So that's at 0 degrees Kelvin. Essentially, that would just cancel out any effects that the change in entropy would have, leaving us with our negative delta H, and thus a negative Gibbs free energy. Now you might ask, why couldn't this be the case if temperature was lower than 0? And it's just important to remember that temperature here is Kelvin, and we can't get below 0 degrees Kelvin, because by definition 0 degrees Kelvin is the complete absence of heat. So just to end in a summary, I guess the important things to take away from this video is that Gibbs free is essentially the term used to describe the amount of available energy there is to do work. And the delta G, or the change in Gibbs free energy, is just the difference in the energy, or the amount of energy, before and after a reaction. And it's important to know that if delta G is negative, this reaction is typically spontaneous. Additionally, if delta G is negative, it's important to know that energy is released from the system, and that energy is actually being lost. So if this video has helped out in any way, it would be really, really great if you guys could just drop a like below. If you have any further questions, or if you have any videos about topics you'd like me to cover, please feel free to just comment below, and I'll try and cover them in a later video. Cheers, guys.